Welcome to another show from Math Animations. Today, we will visit the world of statistics meets differential equations and mathematics. We all know that stats are involved in combinatoric games such as casinos, flipping coins, cards, and the lottery. However, did you know that stats are vital in real business world applications dealing with risk and decision analysis? Queuing, budgeting, inventory control, and project management. All of these deal with uncertain random inputs of data. These processes are called stochastic models. However, because solving these models are extremely difficult, we'd like to transfer these models into something called probabilistic methods. And in order to solve these, we need help from many statistical distributions. To show a probabilistic example in action, we will use the help of systems of differential equations. System of differential equations can be used to describe movements and speed throughout a system. Systems such as hurricanes, water currents, weather patterns, and stock market fluctuations. Today, we will use this simple system of differential equations that simulate outward swirling. We will use random points generated from a prospective distribution to see the probability that the point will end up in a certain quadrant after 1.5 minutes. To better show this, we will use the example of a normal distribution. As you can see from this picture, we have placed random points in or around a unit circle following a normal distribution. This distribution has a mean of 0 and a standard deviation of 1. Now, after running our simulation as shown here, our random points ended up in different places based on this differential system. After doing this simulation with 100 points 500 times via Mathematica, they all ended up almost evenly throughout each quadrant. If you point out from this system, we must have a bias towards certain quadrants. If we were to try to make a guess as to where these randomly placed points on this system would end up, our decision would basically tell us we have no clear guess. However, that differs on other distributions. The next distribution is a Poisson distribution. This distribution causes points to scatter outside the unit circle in quadrant 1. However, due to the nature of this Sorry for the interruption. However, from this moment forward, we will refer to this differential system of equations as Betty. Okay, due to Betty's vector field characteristic, it brings the points in quadrant 1 outside to quadrant 3. Based on this information, I would decide that 58% of the time I would predict right with the guess of quadrant 3. And yes, those who paying attention, 0% for quadrant 1 in the table is supposed to be 16%. For my break, please take a look at these next 3 distributions and analyze what's going on until I return for our great conclusion. Now, we take a look at a special case of distributions. Distributions with mixed distributions. This distribution is a mix of a normal distribution, which we're all familiar with, and a Gumbel distribution. A Gumbel distribution is used to model the distribution of a number of samples of various distribution maximums or minimums. It is a particular distribution of the generated or generalized extreme value distribution. It is useful in predicting the chance of an earthquake, flood, or other natural disaster. In this next case, we will combine this distribution with the normal to get pretty interesting results. Like a Poisson distribution, the Gumbel distribution morphs as your alpha, in this case, gets extremely large. This picture shows a small Gumbel distribution mixed with the normal distribution. As you can see, we get a great amount of scatter throughout the unit circle and the second and third quadrants. However, as you can see in this animation, you have a 44% chance that your points will end up in quadrant 4. As you can see, Betty's characteristics on the outskirts of Q2 and Q3 bring points all the way around to Q4. This combination of gamma and normal distribution brings our points to the center of Betty. However, roughly 75% of these dots are scattered outside of quadrant 1. However, Betty's vortex of fury slings these points on a ride to quadrant 1 60% of the time. From these examples and Betty, it should be seen how certain statistical distributions can affect an outcome of a model. Within this probabilistic model, a decision on how a point is affected by our differential equation model Betty varied greatly based on the random distribution process. On our other examples of stochastic models, queuing, inventory, budgets, and stock markets, one wrong assumption on your statistical model could have you making erroneous decisions that can cost you millions rather than a few lost dots in mathematics. Whoa, hold up, wait guys, wait, not through. Or like one of my favorite wrestlers in the early 90s would say, cut the music! Okay. Oh, that actually felt pretty cool to say. I just wanted to show you guys that I just didn't paste a lot of pictures and steal some movie files. I did a lot of coding, a lot of Mathematica coding, and some Movie Maker and PowerPoint to bring you this project or movie presentation. I'm going to first show you, this is my animate code. I basically can take a differential equations function, any of them. I took Betty and basically was able to animate Betty. And this basically gives you an animation. Took a lot of code, a lot of graphs, a lot of points using to solve, but I pretty much got it done to where it was able to animate what I want. I also use separate files to do your simulations to basically see what my averages were. I didn't get those out of the air, but I actually ran these through Mathematica, and as you can see, I use a lot of distribution functions. Mathematica has a ton of distribution functions. I thought there was just gamma and Poisson, but however, there's like Laplace distribution. Gumbel, I stumbled upon that one, which is pretty interesting, but a lot more. So this takes your equations, it solves it, gives you a nice parametric plot. Hey, I didn't know anything about parametrization. I didn't do that, middle school, maybe like high school, 10th grade, and I'm having to use parametric points again for my simulations and my animations. And to get my plots, here's the code to do plots. I use a for loop, use like a list polar plot. Mathematica has a lot of different functions like for plotting, and I was able to do randomization to get you these plots as you see here, and I was introduced again to polar coordinates, which I haven't probably used since high school, and I really didn't need that, so that was like a headache for nothing, but nonetheless I got familiarized with polar coordinates. The coding was not too bad. I had a lot of files. I had probably 20 plus Mathematica notebook files that I had to manage just to get everything situated. So it wasn't just easy to get this done and code all these in Mathematica. Also, hey, I used Movie Maker. Movie Maker Windows or Windows Movie Maker was quite cool actually. It was free, which made it cool, but in the process it was easy. Yes, I probably cussed a lot, doing a lot of takes on these narrations, and my voice is not naturally deep, so yeah, my voice hurts as well. But it was all in good fun. Had fun doing this project. And there's no, not Mathematica, PowerPoint, and I use PowerPoint for stuff like this as well. So I do have a lot of stuff in my background. There's Movie Maker, a lot of Mathematica code files. I recommend math majors or computer science majors to pick up and learn some Mathematica. It's really good for modeling. And this is really it. Thanks guys for watching, and here's the credits, and hope you enjoy.